I want to next show you some classical examples of applications of Nash equilibrium. One of the earliest examples is the Kruno Duopoly model. There are two firms. These firms compete by setting the quantity that they're going to produce. Firm 1 produces the quantity Q1, firm 2 produces the quantity Q2, and so the total quantity is capital Q, which is Q1 plus Q2. The price is given by the inverse demand, which is P equals 1000 minus capital Q. So 1000 minus Q1 minus Q2. Each firm has a constant marginal cost of 100. How do we formulate this as a game? We first need to write down the strategy sets and then the payoff functions. The strategy sets for both firms are the same. There's a set of non-negative reals. So this would be from 0 to infinity, not including infinity. What's the payoff to a firm? Firm 1's payoff, if firm 1 picks quantity Q1 and firm 2 picks quantity Q2, is the price, which is 1000 minus Q1 minus Q2, times the quantity that firm 1 produces, which is Q1, minus the cost of producing Q1. Remember, there's a constant marginal cost, so it's 100, which is the marginal cost, times Q1. The payoff of firm 2, when they produce Q1 and Q2 respectively, is the same price minus the cost of producing that. So the revenue is the price times the quantity Q2 minus the cost, which is constant marginal cost times the quantity Q2. So these together define a normal form game. Each firm has to simultaneously decide the quantity that it wants to produce. The best response function for firm 1 tells you, as a function of the quantity chosen by firm 2, what is the quantity that firm 1 should choose to maximize its payoff. So it's a solution to the following problem. You maximize your choice of Q1 greater than or equal to 0, the objective times Q1 minus 100 Q1. The first order condition is going to say 1000 minus 2Q1 minus Q2 minus 100 equals 0. In other words, Q1 is 900 minus Q2 divided by 2, which is 450 minus Q2 over 2. So the best response of player 1 or firm 1 to the choice of firm 2 is 450 minus Q2 over 2. If we're being very careful here, we should really write this as a set containing that one element, but whenever there's just one element in the set, we're just going to take a shortcut and just write it this way. If we did exactly the same thing from firm 2's perspective, we would find that the best response for firm 2 would take the same form. Now what we want to do is find a Nash equilibrium. Let's suppose the Nash equilibrium is Q1 star, Q2 star. Then what we know is that Q1 star has to equal 450 minus Q2 star over 2. And Q2 star has to equal 450 minus Q1 star divided by 2. Let's call this 1. Let's call this 2. 2 tells us that Q1 star has to equal 900 minus 2Q2 star. Let's call this equation 3. We can look at equation 3 and equation 1. They both give us expressions where the left-hand side is Q1 star. So by 1 and 3, 900 minus 2Q2 star equals 450 minus Q2 star divided by 2. That means that 450 equals 3Q2 star over 2, which in turn means that Q2 star has to be equal to 300. Let's call this 4. We can plug this in to 3 by 4 and 3. Q2 star is 300, so 2Q2 star is 600. Subtract that from 900, we find that Q1 star is 300 as well. So the Nash equilibrium is 300, 300. You may want to verify here that a total of 600 is not what the monopoly would produce. So these two firms together, because they're competing with one another, are generating less profit between the two of them than they could if they made a joint decision. Again, the recurring theme that the equilibrium is not necessarily going to be the Pareto efficient outcome comes back here. The logic in this one is actually quite similar to the partnership game that we've seen. The next game we'll look at has a different logic when you try to solve for the Nash equilibrium. It's called the Bertrand duopoly model. So unlike the Kruno model, the firms compete on price rather than quantity. So firm 1's price is P1, firm 2's price is P2. The quantity demanded depends on the price, and so the total quantity demanded at the price P is 1000 minus P. Each firm has a constant marginal cost of 100. Now what exactly is the price if the firms set the price P1 and P2 respectively? It's going to be the minimum price. If one firm has a lower price, say PI, it gets all the demand. So 1,000 minus PI is a demand that that firm gets to serve, and the other firm gets no demand. If they have the same price, let's say P, then they just split the demand. So each gets 1,000 minus P divided by 2, where P is a common price. So how do we write this down as a game? Again, we need to specify what the strategy sets are. Each firm has to pick a price which is going to be a non-negative real. Let's write down the payoff of firm I when the firm I picks the price PI and the other firm picks the price PJ. Well, it's going to be 1,000 minus PI times PI minus 100 times 1,000 minus PI. So it's the quantity times the price that they set minus the marginal cost times the quantity. That's if PI is less than PJ. They get no demand and therefore they get no revenue nor do they pay any cost if PI is bigger than PJ. And if PI and PJ are equal, they get half the demand, which is 1,000 minus PI over 2. So their payoff is 1,000 minus PI over 2 times PI minus 100 times 1,000 minus PI over 2. Now we can look for a Nash equilibrium. Let's suppose P1 star and P2 star form a Nash equilibrium. We'll figure out by process of elimination what P1 star and P2 star need to be. First, could it be that anyone sets a price less than 100? That's clearly not going to be profitable because you're getting a negative utility. You can always ensure that you get zero utility by setting a higher price than your opponent. Therefore, anybody who's setting a price less than 100 cannot be best responding to their opponent. What about if one person has a price that's at least 100, as we've seen above, everybody sets a price of at least 100, but the other one has a price that's strictly higher. Could this be an equilibrium? So if we drew a picture, it would look, just drawing this on a line, we've got 100 here, you got firm I is setting its price here, and the other firm J is setting a price up here. Could this be an equilibrium? There's two cases we want to consider, because here we have a weak inequality. If firm I's price is, like in this picture, strictly higher than 100, and firm J sets a price that's even higher, what could J do? Then J's payoff is 0, because they have the higher price, firm I has a lower price, firm I gets all of the demand, firm J gets no demand, so firm J gets payoff of 0. If firm J were to pick some price in here, let's call it PJ prime, then firm J would have a strictly higher profit than 0. So at any price in the interval 100 to PI star, so this notation, remember, means that the boundaries are not included, so anything strictly higher than 100, strictly lower than PI star. Because firm J would be undercutting firm I, firm J would get all of the demand. Moreover, the price would be higher than the marginal cost. So firm J's payoff from picking PJ prime, that's strictly between 100 and PI star, would be strictly greater than 0, which is what their payoff would be from picking PJ star. This contradicts the assumption that we had a Nash equilibrium. So this means that PJ star is not a best response to PI star. So P1 star, so this couldn't have been an equilibrium to start with. On the other hand, if PI star equals 100 and PJ star is bigger than PI star, so in this case we have a situation that looks like this, then firm I is making 0 payoff. Firm I is setting a price equal to its marginal cost, so it's not making any money on anything that it sells. However, for any price between the two, we'll call it PI prime, anything that's strictly higher than 100 but strictly smaller than PJ star, I still gets all the demand, but at a price higher than marginal cost. So, firm I's payoff from playing PI prime rather than PI star is higher. Again, we find that in this case for firm I, PI star is not a best response to firm J playing PJ star. The next situation we can think about is where both firms set the same price and is a price higher than 100. Could this be an equilibrium? Let's draw that picture again. So we've got 100, which is the marginal cost for both firms, and we've got PI star equals PJ star. Just like one of the earlier cases, at any price in here, either of the firms can capture the entire market. So by undercutting their competitor, a firm can capture the entire market and increase its profit. So a firm I can reduce its price by a very, very tiny amount. So think like a penny and capture the entire market rather than just half. So it can more or less double its payoff. The price reduction would be very, very small compared to the increase in demand. The demand would double and the reduction in price would be insignificant, and so the total profit would nearly double. So it can't possibly be that these firms are best responding to each other. That leaves only one possible configuration for the prices. That's where both firms set the same price, and that price is equal to 100. Now let's check whether that's an equilibrium. If my opponent sets a price of 100, there's nothing I can do that's going to give me a payoff that's positive. Any price I set that's at 100 or greater is going to give me a payoff of 0. That means that 100 is a best response to 100. And by similar reasoning, 100 is the best response for J to 100. So we have that 100 is a Nash equilibrium. In fact, it's the only Nash equilibrium. So these were two classical examples of where Nash equilibrium has been applied as a solution concept to understand what happens in a game. I'd encourage you to look at the other examples in Chapter 10 and also work through the guided exercises.